Hello, everyone. This is Zeyuan Shang from Einblick Analytics. Today, I'm going to present our paper, Davos, a system for interactive data-driven decision-making. First, let me introduce our company, Einblick Analytics. It's an MIT and a Brown University spin-off based on the North Star project, which was developed as part of the DARPA DCRM program. We are a pretty young startup, founded in January 2020, located in Cambridge. Einblick offers a visual data computing platform. So visual data computing really defines the way people interact with data through an interactive unbounded canvas. It enables people without data science background to collaboratively work and play with data to take decision actions. And Davos is the backend progressive computation engine of the whole platform, which is in the middle. Here is a screenshot of 3 users working together on a marketing campaign analysis in Einblick workspace. At Mark 1, you can see that they import different data sources. At Mark 2 and 3, they run so-called descriptive analytics through visualizations and statistical methods. At Mark 4, they carry out the predictive analytics to find a good machine learning pipeline predicting the marketing outcome through the AutoML operator. At Mark 5, they use a what-if optimization operator to figure out what's the best marketing strategy to use to maximize the outcome, which is usually called prescriptive analytics. However, existing tools are limited in supporting those analytics in that first, their interfaces are designed based on decade-old concepts and workflow engines and dashboards. And secondly, their backend don't aim to support such complex and often custom operations at the speed of thought. And to address those issues, we design Davos. And first of all, Davos adopts a progressive computation model for interactivity. By progressive computation, Davos basically starts delivering results as soon as possible, and the results will be refined over time. Also, we use sampling for super large data sets to have a good initial result. And the implementation is done through stream processing, where data come in and out as the streams. And the advantage of progressive computation can be huge. On the right side, this shows a quality of a result over time for running a histogram over a 10 gigabyte dataset. The quality is defined as how close the result is to the ground truth. And you can see that we're able to return a result with more than 90% quality within the first 300 milliseconds. And the whole computation takes about 6 seconds to complete. And for most data systems, they adopt a blocked query model, which means you have to wait until the whole query is done before you can actually see any results. And the second aspect of Davos is flexibility without hurting performance. We leverage both C++ for efficiency and Python for flexibility when we are building the system. We design a generic interface for operators, including traditional OLAP operators, like you can do histogram, filter, which all of them are implemented in C++. And we also support machine learning, data mining, AutoML operators. And we also have a user-defined operator. And both of those operators are implemented in Python. For more details, please refer to our full paper. And here are some example operators in Davos. And as we have discussed, we use stream processing. So the operator takes data batches as input and output. And you can see here we have a filter, and the input is a data frame. And we can just return all the, we have filter selecting all the people age over 18. We just return the selected, the filtered data through batch query. And the second example is the average aggregation operator. It's a little bit more complicated because we have to initialize some states in the initializer. You can see that we initialize sum and count, and we accumulate sum and count over time, and we return the current estimated average after each batch. And a more complicated example is a model trainer. And here in the initializer, we create a random forest classifier with the provided parameters, and we train the model through taking the batches as features and targets, and we save the model, and we get a model ID as output. And we have a model executor which takes into the model ID as its parameter, and it loads the model, and in the precise batch function, it executes the model to make predictions over the input batches. And the third aspect is Davos' support for multi-tenancy for promoting collaboration. We basically consider multi-tenancy in many aspects of system when we design it. Firstly, as we have discussed, we use sampling for large datasets, and we have a sample space allocation algorithm to guarantee fairness in terms of space among all clients. And we also have a scheduling strategy which prefers short-running jobs with lower progress to optimize for interactivity for a multi-tenant scenario. And also we have adaptive caching strategy, which will can adaptively cache expensive results based on how frequently are used over all clients. And again, for more details, please refer to our full paper. And here are some implementation details. We do some optimizations for front end. For example, if a visualization, as you have seen in the screenshot, is moved out of screen, we can disprioritize its query in scheduling because the user for now don't care about its result. And also we have a secure user-defined operator mechanism. Basically, each UDO has its own Docker container. So we have so they are fully isolated such that there won't be any security risks to the host machine. And also they have a good hardware resource isolation. And here is the main experiment of Davos. And there are many other experiments in the full paper if you are interested. And here we use a flight dataset, which is 27 giga with 500 million rows. And we run different queries, basically covering all the operators in the system. And you can see that Davos, and we measure the first response time and the last response time, and how long it will take if we just send back a result at the completion. And you can see that for all queries, Davos is able to return a first result within the first 2 or 3 seconds. And you can get better results over time for sure, which is and for the blocking model, sometimes you have to wait several minutes before you can get any result. And so today we presented Davos, which is a progressive computation engine, and it has great flexibility without hurting performance. And we considered multi-tenancy for promoting collaboration. If you are interested, please refer to our full paper for more details. And this is my talk today. Thank you.